Minal Wankhede Barsagade, who is a mathematics teacher at the Mandal College, and would be presenting on contribution of Bhaskaracharya in modern mathematical concept and overview.
Very good afternoon to you all. Myself, Mrs. Minal Wankhede Barsagade from Mandal College, which is actually the part of Vidya Prasarak Mandal, presenting a paper on contribution of Bhaskaracharya in modern mathematical concepts and overview. I am privileged to present this paper during this conference Bhaskara900, which is conducted by our own Vidya Prasarak Mandal. I am glad to present this paper in front of my beloved principal, Dr. Madam. The content of the paper goes like this. The modern mathematical concepts like differential, calculus, integral calculus and the surface area, the interpretation of that in terms of Bhaskaracharya is actually done in this particular paper. Let us have a look on the introduction part. Indian mathematics has its glorious root in the civilization. We need to explore various causes of Latin expansion during ancient and medieval period. The modern mathematical concepts like integral calculus, derivative, spherical trigonometry are considered to be originated by the foreign mathematician Newton, Leibniz, etc. But the book Siddhanta Shiromani, that is the crown of Siddhanta, written by Bhaskaracharya in 12th century, is the true origin of modern mathematical concepts. His work Siddhanta Shiromani is a book basically on astronomy, which contains the preliminary concepts of infinitesimal calculus, mathematical analysis, trigonometry and integral calculus. Bhaskaracharya also goes deeper into the differential calculus and suggests the differential coefficient vanishes at extreme value of the function, indicating the knowledge of infinitesimalism. The so-called golden age of Indian mathematics can be said to extend from 5th to 12th centuries. It has been found that some very advanced mathematical discoveries were made at a very early time in India. Let us have a look on the reason why there is a lack of development in the Indian history, or as far as the history of Indian mathematics is concerned. Very few books are written on the development and history of Indian mathematics. There has been a total lack of attention to the methodology and foundation of Indian mathematics. There is a very little discussion of the arguments by which Indian mathematicians arrive at and justify their results. In the same way, no attention is paid to the philosophical foundation of Indian mathematics, its understanding of the nature of mathematical objects, the nature of mathematical knowledge and the nature of validation of mathematical results and processes. It is often said that no rigorous proofs are advanced in Indian mathematics, while the modern scholars seems to be unanimous in holding the view that Indian mathematics totally lacks any notion of proofs. In fact, some of the results were noted in various European works on Indian mathematics up to the first half of the 19th century. One of the major reasons for our total lack of comprehension, not merely of the notion of proof, but also the entire methodology of Indian mathematics, is the scant attention we have so far paid to the source work themselves. The recently published book, The Source Book of Indian Astronomy, lists about 285 works published in mathematics and mathematical astronomy, of which 50 are works written prior to 12th century AD, about 75 are works written during 16th to 19th centuries. A serious study of even the published work would give us a reasonable idea of the methodology of Indian mathematics and astronomy. we will have a quick look on the development or the background, the history of trigonometry worldwide. The development of trigonometric functions is having rich diverse history. The trigonometry is not the work of one man or a nation. The trigonometry of Ptolemy was based on the functional relationship between the chords of a circle and the central angle they subtend. The writers of the Siddhant changed this to a study of relationship of half a chord of a circle and half of the angle subtended at the center by the whole chord. From this stemmed the predecessor of modern trigonometric functions known as the sine of the angle. So the chief contribution, India and mainly the Siddhanta, is merely the formal introduction of sine function to the history of mathematics. Let us try to have a look on the development of trigonometry in India as well. Trigonometry significantly developed in India in 4th to 5th century. In Siddhant, sine is defined between half an angle and half a chord, while also defining the cosine, versine and inverse sine, where versine means 1 minus cos cosine here. Aryabhatta collected and expanded upon the development of the Siddhanta in Aryabhatiya. The Siddhanta and Aryabhatiya contains the earliest surviving tables of sine values and versine value in 375 degree intervals from 0 degree to 90 degree to an accuracy of 4 decimal places. Bhaskara900 in 7th century produced a formula for calculating the sine of an acute angle without use of a table. Later on, Brahmagupta developed the formula 1 minus sine square x is equal to cos square x. Bhaskara2 in 12th century developed spherical trigonometry and discovered many modern trigonometric results. He is the one who discovered the following modern trigonometric formula, that is sin a plus b and sin a minus b, that we discussed today while teaching the trigonometric to the students here. Indian mathematicians were the first to give a real life application to tangent, relating it to the shadow and heights. By 1150 AD, the ideas of 6 trigonometric functions existed. They were just not named as we know them today. Euler has some input in the development of trigonometry. In his work, sine was no longer a line segment, rather it transformed into a number or ratio. He is the one who has given the name sine, cos, tan, etc. He gave the strict analysis of trigonometric functions. The next thing that we are going to see is regarding the development of calculus in India as well. The Indian mathematician, astronomer Aryabhatta in 499 AD used the notion of infinitesimal and expressed an astronomical problem in the form of basic differential equation. Manjula in the 10th century elaborated on this differential equation in commentary. This equation is usually led Bhaskaracharya to develop the concept of infinitesimal change, and it described the early form of Rolle's theorem. We will have a quick look on the development of calculus worldwide as well. The discovery of calculus is often attributed to two men, Isaac Newton and Gottfried Leibniz, who independently developed its foundation. Newton considered variables changing with time. Leibniz thought of the variable xy as ranging over sequences of infinitely close values. Leibniz introduced dx and dy as differences between successive values. Newton used quantities x and y, which are finite velocities, to compute x and y. Much of the notation used today is due to Leibniz. In the development of calculus, both Newton and Leibniz used infinitesimal quantities that are infinitely small and at non-zero. After 100 years, Cauchy, Weierstrass, Riemann reformulated calculus in terms of rather than infinitesimals. The derivative and integration were reformulated in terms of limit. So now the basic contribution that the Bhaskaracharya made towards the modern mathematical development, we are going to have a look on this. The most renowned Indian mathematician and astronomer before the advent of modern European science was Bhaskaracharya. In his 36th year, he wrote the famous Siddhanta Shiromani having 1443 verses. It consists of 4 parts: arithmetic under the title Leelavati, algebra, that is Bijganit, Goladhyay, spherical trigonometry, Grahaganita, planetary motion. In astronomy, he worked on the idea of instantaneous velocity and discovered the derivative of sin x. Leelavati is modern textbook on elementary mathematics. It includes algebra, geometry, mensuration, permutation, combination, area, volume, etc. In spherical trigonometry, the advanced formula of sin x plus y is found to be proved. We will try to see how Bhaskaracharya was known about the Rolle's theorem before Rolle actually invented it. Let us have a look on this Rolle's theorem. The subject of calculus includes hundreds of theorems and equations that have been derived throughout the centuries. French mathematician Michael Rolle discovered the theorem in 1691. The name Rolle's theorem was given to the basic result by Gasto Bellavides in 1846. Let us look at the statement of Rolle's theorem quickly. As we already know what the Rolle's theorem is, if the function f is continuous on closed and bounded interval, differentiable on open interval, satisfying the condition that f of a is equal to f of b, then the derivative of f vanishes at some intermediate point. In other words, if f is continuous curve that has a unique tangent line at every point of the interval and has the same value at each of the end points, then somewhere in the interval f has a horizontal tangent line. The Bhaskaracharya has interpreted this Rolle's theorem in terms of the equation of center. So we'll have a quick look on the definition of what do you mean by equation of a center. The same planet would sometimes be observed moving faster and sometimes slower. It is this changing motion that astronomical tables have designated as the equation of center. That is, the difference between the mean and true position is spoken as Mandaphala, which corresponds to equation of center. The equation of center in the modern mathematics, astronomy, it is given as 2e sin m. Bhaskaracharya has already interpreted this particular equation of the center where m is interpreted as Manda Kendra, the difference between the longitude of the planet and the Mandocha. The Mandocha means the point where the planet is slowest, and Ucha because it is the highest or farthest from the earth center. And then the Bhaskaracharya's Rolle's theorem. So this evidence of Rolle's theorem in the work of Bhaskaracharya, one can see in the statement which says that when a planet is either in apogee or in perigee, the equation of center vanishes. Hence, he concludes that for some intermediate position, the increment of the equation of a center, that is differential, also vanishes. The instantaneous velocity, derivative and in application in terms of mean value theorem is actually the first evidence in Siddhartha Shiromani. In spite of early evidence of advanced mathematics, the due credit was not given to Bhaskaracharya. We'll also have a look at the evidence of the formula of sin x plus y. The formula for sin x plus y, which is given in verses 21 and 22, it is in the form h sin x plus y. This h is actually the notation for Hindu sign. So that is how we differentiate from the modern sign, trigonometric sign and h sign called as the Hindu signs. We are going to discuss this h sign as well. Let us look at this trigonometry. The Hindu trigonometry we will look at how these trigonometric functions came into existence and how the Indian astronomer looked at this trigonometric value. You can see that the circle with the center at O, you can see the radius to be equal to OB, which is called as Trija. Then you can see the chord BD here. That chord, half of the chord is nothing but BC, and that half of the chord is actually called as the H sign. And then we know in modern mathematics how this sine function is defined. The sine function is always defined as, you must be knowing, the opposite divided by hypotenuse, and then that is actually analogous to that half chord formula which is given as H sign here. The half chord Ardha is itself spoken as Ja for convenience and is the Hindu sign of the R or Cha in. In Hindu trigonometry, angle is connoted by the R corresponding to it and as such spoken as Cha. We'll also have a quick look on how the formula of the derivative of sin x, which we know it as a cos x, how Bhaskaracharya interpret this particular formula in Siddhanta Shiromani. Now since the formula is derived h sin x plus 1, this formula is derived by the Bhaskaracharya like this, h sin x plus h cos x into h sin 1 upon r, and then using this formula the differential h sin x plus 1 minus h sin x is taken to be h cos x h sin 1 upon r, which is equal to h cos x into the constant multiple k here, where h, as you know, it is actually the h sign is representing the Hindu sign here. Let it now be required to find the increment in h sin x for an increment dx in x where dx less than 60. 60 corresponds to the ghati here and 60 ghatis corresponds to 1 ghatika, and since the differential it has to be very small, dx is taken to be less than 60 here, and then you can see that h sin x plus 1 minus h sin x, it turns out to be 60h cos x upon r, which is equal to y, and then you can see that it is multiplied, the expression y is multiplied by dx upon 60, and you can see that we get the expression h y dx 60 is equal to h cos x dx upon r. And hence, if we take the difference h sin x plus dx minus h sin x, which turns out to be the difference in h sin x, which is nothing but h cos x dx upon r, and this is how we can conclude that the derivative of sin x is nothing but cos x. The attention of this particular formula was drawn to the occurrence of this formula by Pandit Bapudev Shastri in 1858. Bhaskaracharya is thus the first mathematician to have pursued this differential formula 500 years before Newton and Leibniz. Bhaskaracharya also has talked about the integral calculus as well, which is the modern mathematics which we come across. How he has interpreted nicely and beautifully, you can see it when we talked about the volume of a sphere. Consider on the surface of a sphere pyramidal excavations, each of a base of an unit area having unit sides as many as the number of unit area in the surface. The apices of these pyramids meet at the center of the sphere. The sum of the volumes of the pyramids is equal to the volume of a sphere. So nicely, this particular concept of infinite sum can be interpreted with the help of this idea of Bhaskaracharya in terms of finding out the volume of a sphere. This result is the nearest approach to the method of integral calculus in Hindu mathematics. It is observed that the modern idea of the limit of a sum is not present, but the idea is of comparatively recent origin of the integral calculus, so the credit must be given to Bhaskaracharya. So I am coming to the concluding part. A lot need to be done to honor the rich mathematical heritage. There is an increasing awareness around the world that as one of the ancient culture, India has attributed substantially to the global scientific development in many spheres, and mathematics has been one of the recognized area in this respect. The country has witnessed steady mathematical development over most part of the last 3000 years, throwing up many interesting mathematical ideas well ahead of their appearances elsewhere in the world, though at times they lag behind, especially in the recent centuries. It is therefore deemed necessary to set forth a brief account of India's mathematical past with special reference to contribution in advanced mathematics, which is anticipation of modern world. I have given you the list of the references over here. Thank you.
Thank you. Yeah.
Brahmagupta is earlier to Bhaskara.
Yeah.
She said
Bhaskara.
later Bhaskara, Brahmagupta has done something. And one more correction, Leelavati, arithmetics, mensuration, algebra, mensuration, extension. If in Leelavati, algebra contains in Bijaganta, which matter was contained?
See, when you look at this Siddhanta Shiromani itself consists of 4 parts, separate parts.
You are telling Leelavati
itself consists of Bijganita.
that contain arithmetics, algebra, mensuration you told.
Yeah.
Algebra is separate in Bijaganta.
Algebra is in Bijganita, yeah.
That's what I will correction. I am not commenting.